Okay, looks like the big hand is on 4, the little hand's on 6. It's 10:02, so it must be time to start.
All right.
So my good friend from Toy Story, Woody, used to say, "To infinity and beyond." I think you're up, Charlie.
Okay. This is kind of a small bore presentation. Using the word bore in this context is probably a mistake, but we were talking about L2 several times, and it's come up. I gave a talk on designing an orbiting space city a couple of years ago, and we were talking about the Lagrangian point L5. We've had there's a solar observational satellite that's up there now at L1, and there's the news recently has been, of course, about the James Webb telescope, which is now at L2. And in some of these discussions, I found the discussions kind of confusing, and had to get my own thoughts straight. And I wondered if there hadn't been some other confusion. One of the things that I was a little slow to recognize, which is my fault, is that when you're talking about Lagrangian points, you talk about them in the context of two bodies orbiting each other. And so as a result, you don't know, until you specify which two bodies are orbiting each other, you don't know what Lagrangian points you're talking about. So for example, we saw recently that the Chinese had put a lander on the backside of the moon, and that then to communicate with Earth, they had to put a relay satellite at L2. And now we saw that the Hubble, the James Webb telescope is going to L2. But the point I wanted to make here is that you have any two you have two orbiting bodies. Binary star can have the same thing, but if you have the Earth-Moon system and you think of it as the moon going around the Earth, then you can talk about the Lagrangian points of the Earth-Moon system. But those are not the Lagrangian points of the Earth-Sun system. The Earth-Sun system has 5 Lagrangian points. The Earth-Moon system has 5 Lagrangian points. In fact, more significant in some ways, the Sun-Jupiter system, again, 2 bodies orbiting each other, they have 5 Lagrangian points. And so that's why I was saying, you gotta be careful when you're talking about Lagrangian points as, sort of whose Lagrangian points? Earth, Sun, Earth, Moon, Jupiter, Sun. And then I always find it kind of confusing when they start telling me that these are the points where the gravitational forces are in balance, because that in fact is not what's going on. The Lagrangian points are, for a given system, let's say the Earth-Sun system, there are 5 points where if you imagine you placed a third massive body of not too massive, a small orbiting body, it will orbit in synchrony. That is, if you think of the Earth going around the Sun, there are points where if you put the third body, it will go around the Sun just in synchrony with the Earth going around the Sun. And that's the significance of those points. But for that to happen, you have to invoke a lot of Newton. Actually, it's a beautiful example of Newton's laws at work, because the first of Newton's laws says that if you have a force, or maybe I'll put it the other way around, if you see a body accelerating, then there must be a force there. And in a way, this is how Newton defines what a force is. It is circular. A force is something that makes an acceleration. If there's an acceleration there, then there must be a force. And that's where you get your F equals ma. He said the force depends on the inertial mass of an object, and the magnitude of the force will be the product of that mass and the acceleration going on. And there's some tricky semantics going on there, because you're defining mass and you're defining acceleration and you're defining force, and you're really defining them all in terms of each other. And the success of the definition is that it turns out to be a really useful way to talk about how things interact. But so you have F equals ma, and then you have Newton's third law, which is that if a body exerts a force on another body, that body must be exerting a force on the first one. And so when you say, and then now comes to Newton's gravitational law, he says that a mass will exert a force on another mass. And he has a nice little simple expression for that. Somewhere I wrote it down. Let me see if I can just pop it up on my screen. Well, I'll have to share my screen. Oh no, I am sharing my screen. So let me.
Hey, Charlie, while you're doing that, you mentioned Lagrange force in 5 a number of times. Is that significant?
4 and 5?
No, that there are 5 Lagrange points in
Yeah,
these various systems you talked about. Is 5 significant?
Well, that's all there are.
Okay, but is that some sort of something that's been proven, that when you get 2 bodies, there can only be 5, or there always are 5, or
Yeah.
5 is the lucky number, or something like that?
Yeah. So let me see here if I can. Am I showing? Yes, this is up. Oh, damn.
And then maybe, Charlie, before you're done,
Yeah.
if you know anything about Lagrange, maybe you can tell us a little bit about where he came from and how he found this stuff out.
Oh, all right. Well, okay. I mean, be careful, you ask your professor to talk, and away he goes. So here is a picture. Does everybody see the picture?
Yes.
Yeah, okay. I just went out and stole a picture off the internet. This is for the sun and the earth. And the picture is a little defective in that L2 is not shown in the picture. So let's see, is that my problem? Let me see.
You
No.
probably cropped that picture.
Yeah, I think I must have cropped it because I think it was there. All right, I'm sorry. But
We'll take your word for it.
all right, but it's I'm embarrassed because it's the one I want to talk about that's missing. It's L2. But so you have a mass m, you have another mass small m, let's say, and then you ask yourself, are there places where if you put an object, it would move in synchrony with what's there? And there are 5 of these places. Now, the issue that I didn't want to get off in a whole lot of algebra. Actually, I enjoy algebra, and I did a lot of algebra in order to prove to myself that I could actually calculate where these points are. But I thought it would be stultifying in the extreme to go on in detail about it. But I did want to try and give you a sense of what it is that you're balancing. And I'm going to do that by stopping share. And I'm going to, let's see, it takes a minute, I guess. Or maybe it's gotten very recalcitrant. My stop share is not stopping my share.
It did stop.
You're stopped.
I am stopped. Oh, okay.
We see the
It just
gallery
takes,
now.
okay. It just takes a while. All right. So then I am going to change my camera to, I did the wrong one. I'm going to change my camera to my USB camera, and then
Yep, we see it.
you should see it. And I'm doing the USB camera rather than sharing, because I tried last time to share, and then there was this latency, which was really quite terrific. I would write something down, and then maybe 5-10 seconds later it would appear on the screen. But I think that this, well, no, there's still plenty of latency there. All right. Anyway, so here's what I had on the other screen. I said, look, you have a mass m, and over here you have a mass little m. And whenever you have this situation in space and one is orbiting the other, then you can talk about Lagrangian points. The Lagrangian points arise because of the properties of centripetal acceleration and circular motion. And I'll come back to that in a minute. So I'm saying that there is out here a point which gets called L2. There is a point here, which is,
Excuse me, am I
reasons-
the only one who's seeing this sort of fuzzy?
It is a little fuzzy.
is it fuzzy? Maybe I should go to share screen and just live with the latency. I'll
But
do
it's
that.
good. At least you can see it.
I think Charlie, it's the camera issue as opposed to latency and
Yes.
stuff. But
Well,
you know, it's just,
I felt my camera was, yeah, that was what Steve was saying last time. And I thought that if I went to this mode,
It's just a focus problem. That's
Yes.
all.
with that, well, let me try. So this is sharing the content from my second camera.
I know. I thought it was good enough.
Yeah, all
Yeah.
right.
exactly.
Right.
Well, then I have,
Just right bigger.
is it? I don't see it at all. Whoop.
Your second camera is showing up as a second view on the screen on the gallery. So it's
Yeah,
there we go.
there we go.
So now you can just use fuzzy logic.
He has 3 cameras. He has a
All
camera on the computer. He has the camera that's facing down and we're seeing shared. And then he has a iPhone or a phone type device.
Well, that's just so that I can see if I'm showing you anything.
And actually, Charlie, it's much crisper now for some
Yeah, I
reason.
thought it was, that's why I went to it. I thought it was, I remembered it as being better. John, you also see that as crisper?
Yes.
Much crisper.
Yeah, okay, good. All right, but I hate this latency
Obviously, the
stuff.
DNA is working.
Yeah,
Yes.
all right, all right. And on the scale of things here, there's a, the scale is very misleading. There's also an L3. So these are all points that lie along the line joining the two masses. And one of the things I would point out right now is, we talk about, for example, the Earth going, let's call this the Earth. We talk about the Earth going around the sun. And so here would be the sun, over here, the big M. And actually, they don't. Now, that is to say, the Earth does not actually go around the sun. It goes around what's called the center of mass. Both the Earth and the sun are circling a common point. The sun is in orbit just as the Earth is, except that the sun's orbit is extremely small. You calculate where is the common point about which these things are going. I mean, this guy is, say, going like this, and the sun is going like that. They're actually going around a point that's inside the sun. It's about 450 kilometers from the center of the sun. And the sun's radius is almost 700,000 kilometers. So you're not very far off the center of the sun. But these are actually measurable motions. We can tell that the sun is going around the common point. We can tell that the Earth is not going around the exact center of the sun. This is also true for the Earth and the moon. That is, the Earth and the Moon, perhaps more significantly, the Moon will go around a point which is at the center of the two, center of mass of the two. And the center of mass, there's some nice formal definitions, but what it really works out to be is there's this little distance here.
Oh, Charlie,
Yeah.
is this true for all planets? I would
Yes,
think
sir.
it would be.
Yes, sir. Yeah. And in fact, it's a good point that you make by asking the question, because the whole idea of Lagrange and the Lagrangian points is approximate. I mean, the Lagrange points exist for two isolated bodies interacting through their gravitational attraction, isolated from all other bodies. There is no such place in the solar system. But if you stay close to the bodies, and two bodies, and far away from the others, it's a pretty good approximation. And so, but you should understand you are talking about approximations, which is what we do a lot of in physics. Anyway, I just wanted you to know that the effect is that there's this distance between the centers of the two bodies, which I'm drawing like that, and so this turns out to be a very important because it determines what the forces are that act. What force does this body exert on this one over here? Well, it depends on the inverse square of this distance, as you all know. You know that Newton's law of gravity is that the force that M exerts, the big M exerts on little m, is equal to the product of the two masses and this constant divided by the square of the distance between their centers. And yet, I'm telling you that they don't move about their centers. They move about a point somewhere inside the body. And I was just about to tell you that the moon and the earth do the same. Now, why? And so here I come to something which I don't know how comfortable people are with this idea of angular velocity, but it's not a hard idea. If you have an axis, a center like this, and you have a point here, and he's going around it in a circle, and I'm sticking with circles, then in a certain amount of time, it will sweep out an angle. And usually in physics, you call the angle theta. But you'll change the angle theta. And you'll do that in a certain amount of time. And that's called the angular velocity. And the reason I want you to think about angular velocity is because what I'm going to try and do is find points L1, L2, and M such that their angular velocity is the same around this center of mass. So that is, you see, if their angular velocity is the same around that center of mass, then say someone's sitting on the Earth here, this point will sweep around the sun and keep locked in synchrony to it. And so you'll see in Wikipedia, a lot of places, you'll see somebody say that these Lagrangian points are the points where the gravitational pull from the sun, earth, and moon cancel each other out. As a result, an object, I'm reading this from Wikipedia actually, as a result, an object located at any of these points will remain in the same location relative to the earth. And this ought to be confusing, at least I find it confusing, because I know that everybody's moving. But I understand that you can go into a moving coordinate system, sort of like if you're sitting on on the inside of a merry-go-round, you look at the outer edge of the merry-go-round, and even though you're both going around, that outer edge is not moving relative to you. And so you have to understand which coordinate system people are referring to, and they're often not clear about that. I like to be out here in sort of the godlike overview, looking down on the solar system and watching it rotate underneath me. And then what I'm telling you is that I want to find point L2, where if I put a mass there, the gravitational attraction of the sun on that mass, plus the gravitational attraction of the earth on that mass, will produce uniform circular motion with exactly the same angular velocity as the sun's attraction on the earth produces of the earth. In other words, it's going to take 1 year for L1, L2, the earth, and L3 to go once around a circle. So that's the whole point, is we're looking for these very special points where the forces, they don't cancel out, they add together to produce exactly the acceleration necessary to produce uniform circular motion that will take you around a circle in 1 year. And that's—
Charlie, do you have to decompose the angular velocity into its orthogonal components in order for this to make sense?
No, that's why I like the angular velocity. I mean, you can do this sort of very elegantly in vector notation, but I don't want to do that. I would like sort of to convey a seat of the pants feeling that what's going to happen, and the way I try to do that is I would like you to notice that what we said before, Newton's law says that F is equal to the mass times the acceleration. Now, the force that the Earth exerts, well, let's see, so I keep going back and forth from Earth to moon, let's go, stay with the sun. The force that the sun exerts on the Earth is exactly the same as the force that the Earth exerts on the sun. The consequences of these two forces are a little bit different. I mean, this is same, F, Newton's law of gravitation, says that the sun is going to produce a certain amount of acceleration of this smaller mass. And what you see is that the acceleration here is going to be, the m's will cancel. So the acceleration is just going to be the constant times the enormous mass of the sun divided by the square of the distance between them. That's exactly the right acceleration to cause the Earth to move in a circle once a year. I mean, that's where it comes from. But if you ask yourself, well, what about the force of the Earth on the sun, on big M? I mean, it's the same force.
One of those accelerations should be capital to
Well, this one
distinguish
is,
them.
I tried to make this one be capital M. And this is tried to be small m.
So he's saying the acceleration, it's hard to see the subscript M and big M and small m on the acceleration.
All right, yeah, okay, so that's
But
again the difficulty with my scale. Okay, but the point I want to make here is that the force that the Earth, little m, exerts on the sun is capital M, the mass of the sun, times the acceleration of the sun. And the two big M's cancel. So even though the forces are the same, the acceleration of the sun is proportional to the mass of the Earth. And the acceleration of the Earth is proportional to the mass of the sun. The sun is the ratio of the mass of the Earth to the mass of the sun. is the Earth is 6 times 10 to the 24 kilograms. The mass of the sun is 2 times 10 to the 30. The result is that ratio is 3 times 10 to the minus 6, 3 millionths. That means that the center of mass distance times the mass of the sun is equal to the ratio of the center of mass to the distance to really almost the distance between the Earth and the sun. That's about 1/3 times 10 to the minus 6. That's about a million divided by 3. It's about 330,000. That's a big number. Or that's not the point. I want to leave you with the understanding that the forces are the same. The accelerations are dramatically different because the masses are dramatically different. So now I'm going to just wave hands here, but I want you to, and if you want me to do something more than that, I can, but I promise to take only about a half an hour and I'm almost there.
Take as much time as you want.
Well, I want to take as much time as I think my audience can bear. Not anyhow.
Nobody's
Charlie-
sleeping
so
yet,
Charlie,
Charlie. You're good.
So Charlie,
go ahead.
if you look at it in any one instant, is there a center of mass that
There
combines
is.
the Earth and the sun, and that's the point?
That's
That's the point at which everything else is, all the Lagrange points are working around?
Yes, that's exactly right, Jerry. That's what I was trying to say. And that point, because the ratio of the Earth's mass to the sun's mass is so small, that point is very deep within the sun. It's only a matter of like 450 kilometers from the center of the sun, whereas the sun is, I think, something like 700,000 kilometers in radius.
So Charlie, can you,
Yeah.
these orbits aren't exactly circular, right? They're a little bit elliptical. Could you talk
Well,
about the effect of how the ellipse
so
especially matters?
all right. So Mitch is asking a good question. The orbits, the actual orbits are circular, are elliptical. The Earth's orbit's only got an eccentricity of about 1%. It is very close to circular. I mean, the most dramatic one is Mars, which is also only a couple of percent, 3%, something like that. You know, Mars, the ellipticity of Mars's orbit is famous because it was enough for Kepler to detect it, whereas it would be really hard to know how in those days measurements were not precise enough to show you the Earth's eccentricity. And you know, it's so for almost all the explanations, it's perfectly satisfactory to treat everything as though it were perfectly circular. If you're gonna fire rockets up there and you're gonna plan sort of orbital mechanics, then you've got to do it numerically. There is no way to do these things in closed form. In fact, it's a famous unsolvable problem of physics called the three-body problem. You can solve the interaction of two masses exactly. A third one, you're stuck with approximations, which is what we're doing right here. And once you get even beyond that, you have to go to numerical solutions. You can't do things, you know, with algebra and vectors. And people, well, I'll leave that. So, but I want you to again to see what's going to happen. So the sun exerts a force on the Earth. You can set it up. It's a perfectly simple piece of beginning physics algebra. You can write down that the acceleration on the Earth is gm over r squared, and that this will be equal to r times the angular velocity. So I just introduced a new symbol because it's the one physicists use all the time. They use Greek omega. That you can think of that as going on in degrees per second, or 360 degrees per year. That's what omega is for the Earth. Physicists use radians. Those of you who know radians would understand this is going to be 2 pi radians in a year. But I want you to see that all you have to do is take Newton's gravitation, the mass of the sun, and divide by the cube of the radius, and you will find that anything that is the distance the Earth is from the sun goes around once a year. That's exactly what the acceleration of the sun on the Earth produces for circular motion. But now look what happens if you go out here. Well, what's going to happen, of course, is the gravitational attraction of the sun, the acceleration due to the sun, is going to drop off.
That's me.
Because you're now farther away from the sun. If you go out, say 10% of the distance of r, the force will drop by about 20%. The acceleration will drop by about 20%. And so this point, look what you actually need. If you're going to be farther away from the sun,
Thursday the 15th
then you're making this r be bigger. And
15th.
that means if you want to go around at the same angular acceleration as the Earth goes around the sun, you've got to produce more acceleration. You wanted omega to be the same, but now r has gotten bigger, the distance out has gotten bigger. You got to produce more acceleration. Well, how can you do that? You're actually, the acceleration due to the sun is dropping. And now you see what the balancing is about. Here sits the Earth, and the Earth is trying to accelerate this mass this way towards the sun, as the sun is trying to do it. And if you go just a little bit out, the Earth's acceleration, the Earth's force on the mass will be plus the acceleration due to the sun will be so great that this thing will have a centripetal acceleration that's too large, and it won't go in synchrony. It'll go too fast. If you go out farther, you will come to a place where the Earth's contribution is just enough to not only compensate for what has dropped by the sun, but adds enough so that the total acceleration on this body will turn out to be this distance from, I don't know, I'm going to mess up my drawing by drawing another great big line all the way out here. And I'll use something like a big script R. You're going to be able to produce the sum of this acceleration and this acceleration will produce a script R omega squared. And that, where omega squared is the angular velocity of the Earth, the one that you're trying to match. So that's what you're doing along here, is you're combining the two forces to produce an centripetal acceleration that's exactly right to give you the angular sweep that you're after. That's the same as the Earth's angular sweep. And there are 3 places. I'm going to have a quiz in a minute. But see, in here, the acceleration due to the sun is going up because you're getting closer to the sun. So this point is going to go too fast, except that this one, the Earth, is got a counteracting force and a counteracting acceleration. The force it's exerting is reducing the acceleration of this point. And there's going to be a point in between the two where the acceleration is reduced to be equal to, let's see, I'm running out of symbols, but I'll just use a Greek rho because physicists love to do that kind of thing. So if this is where this r omega squared will turn out to be equal to, will produce exactly the same angular sweep that the Earth is experiencing and that L2 is experiencing. So that's the argument I wanted to make. And you know, I mean, what I have done. I mean, I can somewhere. I'll just show you the kind of thing that I got into. I mean, and I didn't want to do it with you guys. I thought a morning watching me write symbols very fast, and when it comes out the first time I do it, of course it's wrong, so I have to do it again. And when that comes out, I think I look at it and I say, gee, isn't there an easier way to do this? And so, you know, I do it again. And I must say I got better at it as I did it. But in the end, I'm down to something which is reasonably simple. I am combining two accelerations, one from the sun, one from the earth, to be equal to an acceleration that will be just right to make L2 sweep around. Here's my old diagram of L2 up here. Make L2 sweep around at omega. Now you can do this for the earth and the sun, but you can also do it for the earth and the moon. And big M becomes the earth's mass and little m is the moon's mass. And so if what I've said has made any sense, you should be able to tell me pretty accurately where L3 is going to be. See, I'm saying I got any takers for that?
Just outside the Earth orbit.
This is L3 for the Earth and the Moon.
Yeah.
It's
on your line, but to the left of the sun.
No, that's now the Earth.
So this will orbit. This will orbit similarly to the Moon, but what, 60 degrees ahead of the Moon?
No, now you're getting into you're using exterior knowledge. You're using and you're telling me where L4 and L5 are. I'm saying this is L3.
L3 is that's opposite the Moon.
That's right.
Yeah, exactly opposite. So the new moon would be the full pseudo moon. That's on the opposite side.
That's right. L3. I mean, I hear people, you know, I think you got it. That is, you look out there and you say, well, what acceleration is going to make L3 go around the Earth with the same angular velocity as the moon? And you're on the opposite side of the Earth. You're pretty far away from the moon. I mean, the moon is acting on L3, but so is the Earth. But you're far enough away from the moon, so it's a pretty small effect. It's mainly the effect of the Earth. And we already know what the distance is from the Earth that produces an angular velocity equal to that of the moon. It's the distance of the Earth from the moon. So this distance here is not drawn to scale, but it's going to have to be the same as this distance, the distance across there. That's my story on the Lagrangian points, but I might just recap their utility. The Chinese are using L2 in the Earth-Moon system. And they're using it because they have a lander on the backside of the moon, and there's no way for the backside of the moon to do radio communications to the Earth because the backside of the moon is always away from the Earth. And because the moon rotates on its axis at just the right pace to always keep the backside on the back. And so they have to broadcast, the Chinese broadcast out to a relay satellite, which is out here in a halo orbit. It's kind of going around the L2 point. And if you don't take anything other than this away from what I'm saying, these points are sort of useful for thinking about things, but the actual motions of what's going to happen in those locations require much more refined calculations. They require you to take into consideration the effects of Jupiter and the effects of the ellipticity, the orbits, and all that stuff. And so, I mean, it's a really, it is really quite an amazing evolution of engineering since we first went into space 65 years ago, I guess. Down there.
Charlie?
Yeah.
As sort of a place to wrap things up a little bit, because we do have Drew coming up as well.
I'm ready to stop.
No, that's fine. So looking at the illustration you just did, with L2 on the opposite side of the moon from the Earth, doesn't that mean that the moon is always going to be between the Earth and L2?
No, because the moon is going around the Earth. In the Earth sun system, what we're doing, that's why it's important to know what Lagrangian points you're talking about.
So Lagrange point L2 is related to the Earth as opposed to the moon. So it's the line between, well,
no, see that, okay.
Confusing me.
So I was hoping, as I said, I found this confusing, but if we're talking about the Earth and the sun, there is an L2. It's actually about 1%. It's about 1% of the Earth-Sun distance out to beyond the Earth. That's 1.5 million kilometers. It's a long way, and but that is not the L2 system that is not the L2 point of the Earth-Moon system.
Understood.
Okay, because the Earth-Moon system, of course, is kind of rotating around it, as you know. It's what is it?
But doesn't that mean that you should be able to draw concentric circles with the Earth as the center, with L1, L2, and L3?
For the Earth-Moon, L1, L2, and L3, yes.
So that was my point. So that
I didn't understand, Peter. I'm sorry.
So no, that's okay, and I wasn't clear. So that means that the moon will always be between the two, or is the moon between the two only sometimes?
Well, I mean, think of if you look at this diagram. Let's see. Well, let me. You
have to slide it down a little bit. You lost your diagram.
Yeah. Well, I was okay. Let me redo a diagram. I'm going to put here's. So here's.
The simple answer is that the moon is not always between those two.
That's what I was going to try and get to. So Peter, we have a set of 3 points along this line. Here's the Earth. Here's the moon. And out here there will be L2, and there'll be L1 somewhere in here, and there'll be L3. There'll be L3 right about there. And here's the sun. This whole system is in orbit around the sun. And as it goes, this bar here is rotating once a month. So once a month, what is it, after a week, the orientation will be like that. And after,
I see. Okay. All right.
Okay.
So the L2 and the L2 is related to the Earth-Sun rotation, and the moon interferes with it from time to time.
No, so
I'm missing something.
Yes, yeah, I think so. So this is L2 of Earth Moon. There is a whole nother set of Lagrangian points that have to do with the Earth and the sun.
Understood.
So there's an L2 out here, Earth, sun.
Charlie, make those lowercase L's because they should be distinguished from.
Yeah, but you notice nobody does. when you're looking in the literature, the
Well,
way
I
it's
mean-
being distinguished is here.
Tony, don't confuse me with the facts.
Yeah. Okay, so Peter, now this line that runs from the Earth through the Sun through the Earth-Sun L2, it is rotating in synchrony. All a mass at L2 and the Earth will sweep around the Sun once a year.
Understood.
Okay, and all the while it's doing that, the Earth-Moon system is doing its thing separately.
Okay.
12 times.
And so the L2 around the Earth for the moon is the one that confuses me.
That's the one where the Earth, yeah, you're on the, go
So
ahead.
the Earth and the Sun, you take the Earth and the Sun, replace it with Earth and Sun Earth, replace it with Earth Moon.
Yeah,
And so from what you're saying, it seems that L2 would always be on the, to me, in my mind, because I can't wrap my head around it enough, that L2 would always be on the far side of the moon.
that's correct. No, that is absolutely right. That is in fact why the Chinese have put their relay satellite there.
Okay, so how does the radio wave go from the far side of the moon
Because
to the Earth when the moon's in the way?
So the answer to that is it's not at L2, it's orbiting L2.
That's right. They use what they call a halo orbit.
The halo, because it's a halo orbit, just like the other satellite is a halo.
And
So
it's big enough.
Sometimes, yeah,
It's big enough so it's out of the shadow of the moon.
right. Sometimes, right.
All the time.
All the time.
All the time. Okay, so
It's
the
a
radius of the
million-mile
halo
orbit.
Yeah, the radius of the halo orbit is larger than the radius of the moon. So
Of
it can
the
always go-
shadow of the moon.
the shadow of the moon, correct.
Yeah.
So it can always go around the moon,
Yeah.
if you will.
Yeah.
All right.
Yeah.
That's where I was trying to go, and that's what's confusing me.
All
Thank
right,
you
well,
all.
as I say,
Peter, the humbling part of this is that the sun, the earth, and the moon figured this all out without the help of physicists.
Exactly. But God did a good thing.
Okay.
Hey,
All right.
Charlie, can I ask a
Dick
quick
had a
question
point, and
here?
then we're going to jump
Yeah,
to
go
Joe,
ahead,
if you
Dick.
don't mind.
Conceptually, I understand that if there's a perturbation or a movement of a satellite or a small body away from L1, L2, or L3, that the gravitational forces on that body tend to bring the body back to L1, L2, and L3. Whereas conversely, when you're at L4 and L5, if that perturbation occurs, then the gravitational forces are making it go farther away. In other words, to leave L4 and L5. If that's
No, it's
true,
actually the other way around, Dick.
Yes.
It is?
L4 and L5 are stable for perturbations in any direction. L1, 2, and 3 are stable sort of along the line, but if anything tries to push them to the side, then they don't come back.
Okay, then my question is why?
Again, I mean, it's really just geometry.
Saddle point.
Yeah, and in fact, they are not stable in those positions. They are in equilibrium. But any tiny motion either way, it's going to drive them away from the points.
Well, again, this is L1, 2, and 3. Those are non-stable equilibrium points. You can, if you think in terms of the accelerations, I think if you imagine that you say push the thing out a little bit, then the acceleration that's making the thing go in a circle will diminish so that there's not enough centripetal acceleration for it to keep up, and it will lag behind.
Charlie, would it be
But
easier?
why in L4 and L5 is like a saddle
why are
point
they
that
stable?
comes in?
Yeah, that's historically, you might be interested to know that Euler figured out L1, L2, and L3, and it took until Lagrange came along another couple generations later to find somebody who could explain why L5 and L4 existed even, let alone he discovered them really. And once you're there, you can kind of see what's going on. If you look at where's my diagram? I guess I could go back. I don't know, but you know, I should be.
Charlie, I think the easiest way to reply to this is that when you go through all of the numbers, it turns out that the L4 and L5 are in a potential well or in a concave up curve, while the other three are in a concave down curve.
No, they're actually in a saddle point.
Yes.
They're in a saddle, but I mean, that's good physics talk, and that's what I would say to another physicist. But when I was, you know, I'm trying to give people the kind of gut feeling for what's going on. I didn't really want to get into talking about potential energy and potential energy maps in space.